Have you ever looked up at the sun and felt its power? That distant, burning star that gives us life, but would obliterate anything that got too close. It's a cosmic rule we've always accepted. Don't fly too close to the sun. It's a furnace that melts steel, vaporizes rock, and tears apart atoms with its raw radiation. So what if I told you, do we break that rule? Imagine building the most advanced machine in human history, a multi-billion-dollar masterpiece of engineering, and then deliberately throwing it into the heart of that furnace, because that's exactly what NASA did, to touch it. And somehow, it didn't die. It didn't melt. It didn't get fried into a billion pieces. The sun is not what you think. We look up and see the sun as a calm, glowing disk, steady, peaceful, almost comforting. But that illusion? It's just distance talking. From 93 million miles away, we don't see the truth. Up close, the sun is pure chaos. Its outer atmosphere, the corona, isn't just hot, it's hotter than the surface, defying everything we thought we knew about physics. And yet, this is exactly where NASA chose to send one of the most delicate machines we've ever built. A spacecraft, into the sun's atmosphere. For decades, it was just a fantasy. The numbers didn't make sense. It's over 3 million. No metal, no shield, no machine should survive it. By every calculation, anything we sent should have been instantly vaporized. It wasn't just risky, it was impossible. Until now. Touching the sun without melting. So, how do you fly a fragile spacecraft straight into a 3 million degree inferno? You don't muscle through it, you outsmart it. The answer lies in a strange loophole of physics. You see, there's a big difference between temperature and heat. The sun's corona is millions of degrees, yes, but it's also an incredibly thin vacuum. There are barely any particles to transfer that heat. It's like holding your hand near a flame that's blazing hot, but with almost no air to carry the burn. That's the trick. That's how NASA cracked the impossible. Think of it like this. An oven set to 500 degrees feels hot, but you can stick your hand in for a second without getting instantly burned. Now, try sticking your hand in a pot of boiling water at just 212 degrees. You'll be in the hospital. Why the difference? Density. The oven has very few hot particles to transfer their energy to your hand. The water has trillions, and they all slam into your skin at once. The sun's corona is like that oven. The gas particles are incredibly hot and moving at insane speeds, but there are so few of them that they can't effectively transfer their heat to the spacecraft. So while the probe is swimming in a plasma bath that is technically millions of degrees, its sun-facing side only heats up to about 2,600 degrees Fahrenheit. Now, that's still hot enough to melt steel, don't get me wrong, but it's a temperature that engineering, with a little bit of genius, can handle.
And that's where the real magic begins. The magic of the shield. The unbreakable shield. At the heart of the Parker Solar Probe's survival is a piece of technology straight out of science fiction. Its Thermal Protection System, or TPS. This isn't just a slab of metal, but the real secret is what's on the very front. The sun-facing side is painted with a special, bright white ceramic coating made of alumina. This isn't just for looks. It's a mirror to hell. It reflects over 99% of the incoming solar energy, casting it back out into space before it even has a chance to be absorbed. The tiny amount of heat that does get through is then trapped in a core of ultra-lightweight carbon foam, which is more than 97% space. The result? While the front of the shield is enduring temperatures that would turn a car into a puddle of lava, the back of the shield, just a few inches away, stays at a comfortable 85 degrees Fahrenheit, room temperature. In one test, engineers pointed a blowtorch at one side of the shield material until it glowed white hot. The guts of the machine. But not everything can hide. To study the sun, some instruments have to stick their necks out. They have to face the fire directly. It's completely exposed. So how does it survive? It's built from materials that feel like they belong on an alien warship. Its body is made from a titanium, zirconium, molybdenum alloy, a metal with a melting point over 4,200 degrees Fahrenheit. The tiny electrical grids that measure the solar particles are made of pure tungsten, which can withstand over 6,100 degrees. And its wiring? The wires are made of niobium, a metal so exotic it has to be sheltered inside tubes of pure sapphire crystal to keep from melting. This isn't just a machine, it's a monument to material science. But even with these miracle materials, there's still the problem of powering the probe. The solar panels can't hide behind the shield. The solution is ingenious and terrifying. As the probe gets closer to the sun, it retracts its solar panels, pulling them back into the shield's shadow until only a tiny sliver is left exposed. And that tiny sliver is cooled by its own circulatory system. The probe pumps pressurized, deionized water, yes, water, through special radiators to pull the waste heat away, keeping the panels from frying. And what if something goes wrong? There's no joystick on Earth to fix it. The light delay is almost 8 minutes. By the time a warning signal reached us, the probe would be dead. That's why the Parker Solar Probe has a mind of its own. A network of sensors on the edge of the shield acts as a nervous system. If they detect even a sliver of direct sunlight leaking past the shield, the onboard computer instantly fires the thrusters to correct its position. It's a robot pilot with reflexes faster than any human, constantly dancing on the edge of a razor.
What the sun is telling us. So we built this indestructible messenger and sent it into the fire. It survived. But what for? What secrets is it sending back? The Parker Solar Probe isn't just on a joyride. It's solving some of the oldest mysteries in astrophysics. And where does the solar wind, the stream of particles constantly flowing from the sun, get its incredible speed? Parker is finally giving us answers. By flying through the solar wind's birthplace, it discovered that the wind is energized by bizarre magnetic explosions and powerful waves that kick the particles to incredible velocities. It turns out they originate from deep within the sun's atmosphere, in magnetic funnels on the surface. These aren't just academic curiosities. These phenomena are the engines of space weather. The same forces that Parker is studying up close are the ones that can send devastating solar storms toward Earth, capable of knocking out our power grids, destroying satellites, and disrupting all global communications. The probe's discoveries are a warning. They show us how violent and unpredictable our star truly is. We've been living next to a sleeping dragon, and Parker is the first one to dare to poke it and see what it's dreaming about. Messages from the fire. So here we stand. A human-made object is right now surfing the atmosphere of a star, protected by a sliver of ceramic and carbon. It's a machine built of impossible materials, cooled by water, and steered by a robotic brain, all while moving faster than anything in history. It survived not by fighting the sun's heat, but by understanding it. By finding the loopholes in physics and exploiting them with breathtaking engineering. The Parker Solar Probe is more than just a successful mission. It's a statement. It proves that there are no places in the universe that are truly off-limits. It shows that with enough curiosity, bravery, and ingenuity, we can overcome even the most extreme challenges the cosmos can throw at us. The sun is talking. Through magnetic waves, through bursts of energy, through the secrets carried on its wind. And for the first time, we have a translator right there in the fire with it. If your mind is as blown as ours, hit that like button and subscribe for more deep dives into the technology that's pushing the boundaries of human exploration. This is just the beginning. The probe has years left in its journey, and it's going to get even closer. What other secrets are waiting in the heart of our star? Until then, stay curious.